This video is on section 3.2, measures of variation. So in this chapter, we're studying some computations for how we can kind of analyze our data. And in section 3.1, we talked about measures of center, so we could see where the data was. Here, when we study measures of variation, we're going to study how much the data, each data point varies from the other, what the spread of the data is, what maybe typical data would look like, and how far above and below that they could be. So there are three different methods we're going to look at: the range, standard deviation, and variance. And standard deviation is kind of the most important one. It's the one that we're really going to focus on. So first, the range of a set of data can tell you about some of the variation. It's the difference between the lowest and the highest values. So this is a quick computation. You can just look at your data set, find the highest value, the lowest value, subtract them. But this is really susceptible to outliers. This is not resistant. We learned that term previously. This is not resistant. Meaning while you can get this information quickly, it's not necessarily a good measure of variation. The second method is a bit more time consuming, especially if you're going to calculate it by hand, which we're going to do, but it's a lot more accurate. So the standard deviation, which we will use S to abbreviate that, it measures how much the data varies from the mean. And remember, the mean is the measure of center specifically that you get when you add up all the pieces of data and divide by the number of the pieces of data. So this is the formula for standard deviation. This is sigma. It just means you're adding a bunch of things up. X represents an individual data point. X bar represents the mean. N represents the number of data points that you have, and so n minus 1 would just be one less than that. And so the way that you calculate the standard deviation by hand using this formula is that first you find the mean of the set of data. First you find X bar. Next, you make a chart with three columns. The first column is just the data, just the X. The second column is the data minus the mean, the X minus the X bar. And the third column is data minus mean squared, which would be the X minus X bar squared. So three columns, one for each of those. The next step is to fill in the chart, do all those computations, some subtracting, some squaring, and then you have to do the sigma part of the formula, which means you have to take that third column where you've done the data point minus the mean and squared the difference. You have to sum all of those numbers together to get the sigma part of the formula. Last, you're going to divide the sum by n minus 1, where n is the number of pieces of data, and then you're going to take the square root of the whole thing. And at that point, you will have the standard deviation. All right, so we are going to practice that. And depending on what technological tools you use, there are ways to do that in a calculator. So as you're practicing this on MyMathLab, make sure that you can do this process by hand, because that's something I will ask you to do in a testing situation, is to draw out the chart, do all the computations, show me that by hand you can get it. But it's also great to learn how to do it in a calculator. And so I'll show you that too. All right, so, and I think there's also another instructor mentioned that there's something like StatCrunch on MyMathLab, but I haven't explored that further. So there should be a way to do this in MyMathLab as well. All right, the third method is variance. The variance of a set of values is another measure of variation, which is equal to the square of the standard deviation, and so you denote that using S squared. And if you compare the two formulas, I mean, they're almost identical. It's just that this one is S and this one is S squared. So where this one has a square root sign over it, this one does not, because you've squared it. So you can find those pretty easily together. So the round off rule for measures of variation is to carry one more decimal place than is present in the original set of data. That's good to know because in a lot of cases when you're dealing with numbers here, you're not going to have integers, you're not going to have whole numbers, you'll have decimals to deal with, and so it's good to know kind of how to handle that. Okay, so let's go ahead and look at this problem. We've dealt with this scenario before, data set 33 in Appendix B in your textbook. There's even more information if you look. The author of the textbook has a statistics site where they have just like big files of like all this data that they've gotten. And so what we did is I took the first 11 wait times for Space Mountain at 10 a.m. and this is what they are. We've worked with them before. And we're going to find the range and then we're going to find the standard deviation. So the range is not going to be too bad. It's just going to be the highest number minus the lowest number. So 75 minus 20 is 55 minutes. So that's one measure of variation, that the range in the data is 55 minutes. The other, we're going to go through and calculate the standard deviation by hand. So for our three columns, we have data, data minus mean, data minus mean, and data minus mean squared. So data is just x. You can see that I've already filled that in for you. Next, we'll do x minus x bar. That's data minus the mean. And then we'll do x minus x bar squared, data minus the mean squared. So first we have to calculate the mean. So I'm just going to add up all these values. So we have 430, the sum is 430. And then we divide it by the number of pieces of data. That's the formula to find the mean. So divide that by 11. And then we do just one more decimal place. That was from the measures of center. Notes, similar as the round off rule here, you just do one more decimal place than your data points. So instead of a whole number, we're going to do to the 10th place. So this is approximately 39.1 minutes. Okay, so now we're going to go through and do the data point minus the mean. So 50 minus 39.1, 10.9. And then I'm going to square that, 118.81. And here I'm just leaving the 118.81 because this is kind of an intermediate step, and I'm just going to use that when I add up my sum. So here I'm rounding to one decimal point, just as a way of not writing down everything. But here, I can write down the decimals, and that won't take me extra work. Okay, so for the next one, I've got 25 minus 39.1. And then squared, so negative 14.1, and then 198.81. There's my next two computations. The ones that I already know I'm not going to do twice. Okay, so I've got all my x minus x bars, all my x minus x bar squareds. And so now the next step, I found the mean, I made a chart with 3 columns, I filled in the chart. Now I'm going to sum the values in the last column. So I'm doing the portion of the formula that says find the sum of x minus x bar squared. So I'm going to add up all of these. Okay, so that adds up to 2,740.9. When you're doing something like this, I'd always add them up twice. The reason I'm not doing it is because I added this up ahead of time. So I know that's the right answer. Okay, so there's our sigma of x minus x bar squared, and I'm going to be dividing that by n minus 1, which is 10. So I'm going to have the square root of this number over 10. And that's going to be my standard deviation. And like the rounding tip said, we're going to do 1 decimal place, so 16.6 minutes. Okay, and throughout later in the notes, we'll look at a little bit more about what standard deviation means, like how you can see that within the data, but first, that's how to calculate it. All right, now I said that I would show you how to do it in a calculator, so I'm going to do that. But like I said before, I would not recommend doing this on every single problem on MyMathLab, because if you do it in a calculator, in a testing situation, you'll know that you got the answer right, but you have to do this work to get full credit. And doing it in a calculator and getting the right answer would get you, like, honestly nothing. It's the work that would get you the credit. So, but this is a good way to check your answer, and if you get tired of doing the problems and you want to do a couple of them quick, you can do it this way. So you're going to hit the Stat button on a TI-84, and then you're going to Edit, and we're going to type in our list of numbers. Oops, we're going to type in our list of numbers that we have. So 50, 25, 75, 35, 50, 25, 30, 50, 45, 25, 20. Okay. Then you're going to hit Stat again, and you're going to go to Calculate, so to the right to Calculate, and we're just going to calculate one variable statistics. So it's saying use the information from the first list. Yep, that's what we want. You can ignore the next part, and we're just going to ask our calculator to calculate it. When you do that, X bar, it gives you the mean. And then down here, you can kind of ignore the rest of it. We want S, the standard deviation, which is 16.6. So there you go, there's your information. And then it tells you it used 11 pieces of data, so that's a good way to check, like, oh, I didn't miss one of my data points. Okay, so that's how you do it on a calculator. All right, on the next page, you can see the range rule of thumb, which says for many data sets, the vast majority of sample values lie within 2 standard deviations of the mean. So this is kind of the first thing we see as like how the standard deviation can be used to explain the variation of a data set. So if you start with the mean and you add or subtract 2 standard deviations, that gives you a range of values values that are typical or that are usual to represent that data set. Anything outside of that range would be your outliers. So this is the first time we've had like a numerical sort of standard or a mathematical standard of how we could calculate an outlier, as opposed to just looking at a data set and saying like, that number seems pretty high, or that number seems pretty low, they're probably outliers. Now we can say, well, it's outside of 2 standard deviations from the mean, so it's probably an outlier. So that's kind of the benefit there, and that's called the range rule of thumb. The next thing that we'll talk about is the coefficient of variation, which describes the standard deviation relative to the mean, and it discusses that as a percent. So the way that you calculate it is you do the standard deviation divided by the mean, which just says what percentage of the mean that standard deviation is, and then when you multiply it by 100, you're taking the percentage written as a decimal, and you're just writing it as a percentage. So this allows us to compare variation in samples with different units, such as height and weight of men or women or whatever you're studying. So if you were comparing height and weight, those are 2 different units of measurement. You have pounds and you have inches and feet, or just inches if you're talking about small animals or whatever, and you could compare what percentage of the mean each one of those values is, as a way of comparing how close they are to the average, is what we as lay people would think of it. Not a statistician, they would not use that word average, but it's a way of comparing them. It also allows us to compare samples with significantly different means, even if their units of measurement are the same. So another way you could compare is if you're discussing gymnasts and sumo wrestlers. So if the standard deviation was 3 pounds, 3 pounds divided by the mean for a gymnast weight is much different than 3 pounds divided by the mean for a sumo wrestler weight. That standard deviation means a much different thing if you're talking about a gymnast who doesn't weigh a lot versus a sumo wrestler who does. So it might be a lot more variation in a gymnast, and a sumo wrestler would be not much variation at all, and you would be able to see that by looking at the coefficient of variation. So again, we have a round off rule that I've included here because I always like to know how far I should round. So it seems like, generally speaking, 1 decimal place seems to be what you're going to do. If we're discussing something where it's a whole number, then you should round to 1 decimal place to give it a little bit more accuracy when you do a computation. Or here, when we're talking about something that's just percentages in general, then they're saying give it a percentage with 1 decimal place. So, all right, next we're going to talk about once you have your data and you have it, out here in graphical form, we can see that along the x-axis, we would have some sort of measurement, whether that be weights or heights or whatever. Along the y-axis, we can see that's the frequency. And so this is your normal distribution. This is your bell curve, where all those that are in the middle are kind of more frequent, more often. Those data pieces show up repeatedly. And then these extremes, someone who is extremely tall or extremely thin, those are kind of your outlier values out here. So here's our normal distribution, and we're going to learn about the empirical rule, which kind of describes a normal distribution. So in a normal distribution, approximately 68% of the data lies within 1 standard deviation of the mean. So if the mean is right here, x bar, then you have x bar plus the standard deviation, x bar minus the standard deviation. And between those 2 values would be 68% of the data. All right. Approximately 95% of the data lies within 2 standard deviations of the mean. So over here we've got 95% of the data. And so if you think about the rule of thumb, the range rule of thumb, this is the range of the usual values. Anything beyond this, anything beyond that would be considered an outlier. All right, and then approximately 99.7% of the data lies within 3 standard deviations of the mean. So that would be X bar plus 3 standard deviations over here, X bar minus 3 standard deviations over here, and that would be 99.7% of the data values. All right. So let's look at some examples. These here are some summary statistics. So it's not each of the pieces of data, but some data about weekly salaries at some company was given, and then from that data they calculated the mean, median, and mode, and they calculated the standard deviation. So we're going to answer some questions. What is the most common salary? That's the definition of mode. It's the salary that shows up most often. So that's $735 per week. What salary did half of the employees exceed? That's the definition of the median. The median is the salary that's right in the middle. So half of the employees were below and half of the employees were above. So the median was $710 per week. If the company has 100 employees, what is the total weekly salary of all employees? So this is saying all the employees, so sigma X is saying to add up all of the pieces of data, and this is related to the mean. If you add up all of the pieces of data and divide by the number of pieces of data you have, you end up getting X bar, which is the mean. So if we do the total, which is what we're trying to solve for, divided by 100, we would end up with $740. So we'll just take the 100, multiply it over here, and we get $74,000. So that's the total weekly salary of 100 employees. What salaries would you classify as unusually high? This is where we can use that range rule of thumb. Unusually high salaries would be the mean plus 2 standard deviations. Anything above that would be considered an outlier. And so that's 740 plus 2 standard deviations. So 740 plus 80 is 820. So anything at or above 820 a week is unusually high. Okay. Between what two values do 68% of the salaries lie? So this is the mean plus or minus 1 standard deviation. So the mean minus a standard deviation, the mean plus a standard deviation. So that's going to be $700 a week to $780 a week. 68% of the data is between those two salaries. Okay, use the empirical rule to draw a diagram that describes this data. So along the x-axis, we would have salaries listed in dollars. Units are dollars. The mean is 700. So we're going to add one. Nope, it's not 700. Sorry, it's 740. Okay, so we're going to go up and add 1 standard deviation for each line, 780, 820, 860. And then we'll go down and subtract a standard deviation for each line, 700, 660, 620. And then along the y-axis is just the frequency. So The mean is the most common weekly salary we would expect to have, and then less common as we go out to the sides. So here's 68% of our employees are in between those salaries. 95%. And then 99.7%. Okay. All right, so here it says, consider the resting heart rates of a sample of individuals. The data is normally distributed, so we're going to use the empirical rule, with a mean of 70 beats per minute and a standard deviation of 15 beats per minute. Find the approximate percentage of people whose resting heart rates are in all these following categories. So first, I'm just going to kind of fill out my little table here. You can see I actually drew a line down the middle. You'll see why I did that in a second. So I'm going up by 15, down by 15. Okay, so the empirical rule tells me that between these two values is 68% of the data. Well, if I take 68% of the data and divide it in half so I can see what is in each section of this, then I can see that each of those sections is 34% of the data. And it's beneficial to break this up because now, instead of saying, okay, 68% of the data, it has between 55 and 85 beats per minute, I can say, oh, 34% of the data is between 55 and 70, and 34% of the data is between 70 and 85. So it's allowed me to become a little bit more specific. As I fill out each of these sections with their percentages, I will be able to answer these questions and say what percentage of the data is in any combination of these categories, as long as it's one of these numbers on the bottom. If they use a different number, then that's a whole different mathematical procedure. Okay, so 68%, we've got 34 and 34. The next one is 95%. So I'm going to say 95%. Take away 68%, there's 27% left over to split between these two sections. So I'm going to take 27% and split it in half, and I get 13.5%. And so each of these little sections is 13.5% of the whole thing. Okay, then one more standard deviation out tells us that 99.7% of the data is between those values. So that minus 95 is 4.7%. So I have 4.7% that I can split between this and this. So 4.7, split it in half, and I get 2.35%. So this is 2.35%, and this is 2.35%. Okay, so that was 99.7% of the data. Now over here, these little tails off to the side, the whole thing is 100% of the data. All of the data is going to be drawn in the graph. So the whole thing is 100% of the data. 3 standard deviations is 99.7% of the data. So that means I've got 0.3% of the data left over for those little pieces on the end. And 0.3 divided by 2 is 0.15. So those little pieces on the end are just 0.15%. All right, now these percentages we just found apply to every normal bell curve. 34, 34, 13.5, 13.5, 2.35, 0.15. So you can memorize them if you want. These are kind of the acceptable values that people often use. Or if you just want to memorize the 68, 95, 99.7, then you could just do the mathematical breakdown each time. It is up to you. Okay, so now we're going to kind of look at these and we're just going to calculate what percentages answer the question. So what percentage is less than 55? So 55 is right here. I'm going to add 13.5%, 2.35%, and 0.15%. 16%. Okay. The percentage that is greater than 85, 85 greater than, it's the same numbers, it's just the other side of the bell curve. So 13.5, 2.35, 0.15. That's 16% as well. Okay. Greater than 40. 13.5, 34, 34, 13.5. So I'm just going to add all those up. $97.5. Between 55 and 85, 34, 34. That one's 68. That was easier. Between 85 and 100, 13.5%. Less than 40, 2.35 and 0.15. 2.5%. Less than 85, so from here down, $84. Less than 100, okay, so it's what we just had, it's 84 plus a little bit more, 97.5. Between 55 and 100, so 68 plus 13.5, 81.5. Greater than 70, well, that's just half. It's the right half, so that'd be 50%. Okay. Yeah. I should have said heart rate to label my x-axis down here, heart rate. Units are beats per minute. A lot of people don't label those, but it's, you know, it's good practice. Okay. The next example says the waiting time in seconds of customers at a particular bank are recorded below with two configurations. A single line or individual lines. So when they say a single line, they mean that when you walk into the bank, everybody gets into one line, and then when it's your turn, you go to the individual teller who just became free. Individual lines means that when you walk into the bank, you just look at the different tellers that are working and you line up, you know, you pick the line that's the shortest. So what they have here is they took some data, they timed people and how long they had to wait, and that's what this table is, all their wait times. So here we found that the mean for the single line is 429 seconds, and the mean for the individual lines is 429 seconds. So the means are the same. Or the measure of center is the same. But over here, for the single line, the standard deviation is 28.7 seconds. Over here, the standard deviation for the individual lines is 109.4 seconds. So compare and contrast the two. Which would you recommend? What would you recommend? Well, that's a opinion question. That's what you personally prefer. But there is one thing that should be apparent in your answer when you're answering an opinion question, and that is that you understand what the data is telling you, and you understand what these computations have told you. So what this computation tells you, with a standard deviation that is small compared to this one, is that there is less variation. When all the people are in line in a single line and they just go to a teller who is open whenever they open up, those customers are getting a similar experience. There is less variation in their wait time. They're getting a similar experience. They're waiting about the same amount of time, generally speaking. Over here, there is more variation. So These people, when they're coming and they're just choosing, they're looking and they're saying, I can psychoanalyze that person based on the hat that they're wearing, and they seem like somebody who would only have one quick thing to ask the teller and then they're going to be done. So I'm going to line up behind them. Or that person looks like they're going to take a long time, so I am not going to line up behind that person. Whatever. When people line up in the individual lines, there tends to be more variation. So when you describe whichever answer you would go with, you should be able to use these values to kind of back up your answer. It shouldn't be, I just prefer individual lines, I prefer single lines. You should speak to the variation. You should speak to customer satisfaction maybe prefers that customers in general have a similar experience. And so I would prefer the option that has less variation. I think that's more fair. Or maybe you would say, I think individual lines are better so that people who have more patience and really don't mind waiting, they can choose to, get in a longer line and wait or whatever. And then people who are in a rush can kind of, get into a faster line. It's fine for you to have a difference of opinion, but just make sure that you can use the data present to back up that opinion in a way that is mathematically accurate. That's the important thing. So I think that most people here would probably recommend the single line due to less variation. But if you were able to back it up with good reasoning, then the other option would work as well. All right, the last thing on your notes is this part down here, which just reminds you of some of the notation of statistics. So we have samples versus population, and then the resulting statistics, the resulting numbers that are statistics, and then the resulting numbers that are parameters. So we are not often talking about the whole population. Usually there's a population we want to study, and it's not feasible to study every single person in the population, and so we usually get a subset. And then we study them, and that's a sample. And so we are usually getting statistics. We're usually going to have X bar for our mean. We're usually going to have S for the standard deviation. It is possible, however, for a problem to give you information and say, hey, this actually represents the entire population. And if that's the case, they're going to give you these two variables. This is the Greek letter mu, M-U, mu. This is the Greek letter sigma. And you're like, wait a second, we've already seen sigma. And you have seen uppercase sigma, which means to add up a bunch of things. This is lowercase sigma, which means standard deviation. So I just wanted to point those out so you guys could see the difference and when they'll be used, but we will typically stick over here just because population doesn't show up as often. It's just not as common.